We're going to discuss hyperbolas in this video. They are the final type of conic section that we will come across in our course. We'll discuss the basic definitions of and characteristics of hyperbolas in this video, and then we'll go on to discuss a couple of problems in the following videos, and that will finish our study on conic sections. So what is a hyperbola? Probably new to you, to those of you who haven't done further maths before. A hyperbola, roughly speaking, looks like this. You've got a C shape and an inverted C shape that are sort of back to back with a gap in between. Obviously that's a very crude and rough way of thinking about it, but my objective is to try and convey to you what hyperbolas look like graphically. Alright? Now, so that's the overall shape of the hyperbola. At least in the case of the standard hyperbola, this is how it will look. What are the features we concern ourselves with? The first feature is the axis, okay? The axis is the minimum distance between these two curves. So in the case of this hyperbola, the axis might be somewhere here. A horizontal line joining up these two curves, which would be the minimum distance between them. In this case, the axis is horizontal. Now, I'm going to take a slight tangent here. Let's discuss a possible non-standard hyperbola. Okay, this is probably what a standard hyperbola would look like. But in exams, you might come across hyperbolas which look like this. Overall, they're the same sort of graphic shapes, except it's not a rightward and leftward facing C. It's an upward facing C and a downward facing C. Now, when this happens, the axis of this hyperbola is not going to be horizontal, it's going to be vertical. Okay? The shortest distance between the two curves of this hyperbola would be a vertical line. So unlike this case, the axis here would be vertical, not horizontal. That's something we wanted to discuss. The next feature, the center. The center lies in the middle of the axis. In the case of the standard hyperbola, the center is 0, 0. And in the case of a non-standard hyperbola, again the same principle would apply. The coordinates may not be 0, 0, but the center would still be halfway across the axis of the hyperbola. A hyperbola only really has one axis. It doesn't have any other axes except for the shortest distance between the two curves it has. Alright? Now I'm going to take a slight tangent again and discuss the equation of the hyperbola. This is the standard equation of the hyperbola. X squared over a squared minus y squared over b squared is equal to 1. What does this equation actually mean? Well, it's a bit difficult to explain without discussing all the other features of the hyperbola, but let's take it one step at a time. No matter what hyperbola that you're talking about, whether it's standard or non-standard, x and y will always refer to the coordinates of the points on the hyperbola. So x and y will be variables. The number 1 will always be a constant. And that's irrespective of what hyperbola you're talking about. X and y will be variables, and 1 will be a constant. What do the x denominator a and the y denominator b refer to? Well, that actually depends on the axis of the hyperbola. If the axis is horizontal, as is the case with the standard hyperbola, then the x denominator a refers to half the length of the axis. Alright? So in this case, a would be this half length here, the distance between the center and the curve along the axis. In the case where a hyperbola has a vertical axis, like this, b would refer to half the length of the axis. So in this case, b would refer to this distance here. Alright? So in this case, a would be half the length of the axis. In this case, b would be half the length of the axis. You might be thinking, well, okay, but we've missed out a constant in each of our explanations. In this case, we didn't explain what b was, and in this case, we didn't explain what a was. And that will come into use when we explore the other features of the hyperbola. So let's set that constant aside just for the time being in each of those cases. We'll discuss those later on. Directrices and foci and eccentricity. We've come across eccentricity before when we did ellipses. We discussed before that eccentricity is a ratio, and you can see what the definition of ratio is in the previous video that we covered on ellipses and the basic characteristics of ellipses. The eccentricity of a hyperbola is always more than 1. That applies to all hyperbolas. Eccentricity will always be greater than 1. Alright? Now, another two features we concern ourselves with are the directrix and the foci. The directrices of a hyperbola are always perpendicular to the axis and are equidistant from the center. And they always lie between the center and the curve. So in this case, to draw a rough drawing, let's remove that label for a moment. This might be one of our axes, and this might be the second one of our axes. They're vertical because they have to be perpendicular to the axis, which in this case is horizontal. They are meant to be equidistant from the center. So this distance here should be the same as this distance here. And the directrices always lie between the center and the curve. Alright? So, we've discussed now the directrix, and now we're going to discuss the focus. The focus actually lies farther from the center than the curve does. So, and they would always lie on the major axis if it were extended. Okay? So we're going to discuss, so let's just illustrate what the foci would look like. Let's extend this axis slightly. Obviously, we don't extend the axis. By definition, the axis is the minimum distance between the two curves. But just for the sake of illustration, let's just extend the axis to illustrate where the foci would lie. The foci would always be equidistant from the center, and they would be farther away than the curve of the ellipse. So in this case, this could be one of our foci, and this could be the other foci, and they would be equidistant from the center. This distance would be the same as this distance. In the case of a non-standard hyperbola, which has a vertical axis, directrices would be horizontal, and they would lie between the center and the curve. They would be horizontal, obviously, because they have to be perpendicular to the axis, and the axis is vertical. So let's draw a rough diagram of a couple of directrices there. And as always, they are equidistant from the center. So this distance here is the same as this distance here. And the foci would again lie on the hypothetically extended axis and would be farther away from the curves of the hyperbola from the center. Alright? So if this is our center, this distance between the center and this focus would be the same as the distance between the center and this focus here. The foci tend to be sort of farthest away from the center of the hyperbola. Now, how now do we find the coordinates of the focus, and how do we find the equation of the directrix? Well, we talked about eccentricity always being more than 1 in the case of a hyperbola. Right? So, just to illustrate here, the directrices will always be A divided by E units away from the center, where A refers to half the length of the axis. Just to stress again, A, when we talk about directrices, does not refer to half the length of the, it does not refer to the x denominator, it refers to half the length of the axis. So the distance between the center and the directrix will be A over E, and that will enable us to calculate the equation of the directrix. In this case, because in this case B represents half the length of the axes, B represents half the length of the axis of the hyperbola. This directrix would be B divided by E units above the center vertically, and this directrix would be B over E units below the center vertically. Right? So they will be symmetric. What about the coordinates of the focus? Well, in this case, the focus will always be A multiplied by E units away from the center. Alright, so let's just illustrate that here. Again, A refers to half the length of the axis of the hyperbola. So in this case, this point, this focus here would be A times E units away from the center in this direction. and this focus would be a times e units away from the center in this direction, and the foci, as we mentioned, are always equidistant from the center. In this case, the foci would be be units below the center in this direction, and the other focus would be be units above the center in this direction. And we're using b in this case, obviously, because as we mentioned, in this case, b refers to half the length of the axis of the hyperbola. So now we've discussed the basic shape of the hyperbola, the axis, the center, and some of the features of directrices and axes, and foci. There's only one axis in the case of the hyperbola. So there's one more feature that we need to cover before we jump into some problems. This may seem a bit complicated, but it will sort of come to light with practice, and hopefully should be clearer once we do a couple of problems. The final feature we concern ourselves with is the asymptote, or asymptotes of the hyperbola. These curves here of this hyperbola don't go on forever. They actually stop at the ellipses. At the asymptotes. Sorry, my apologies. Alright, so the two directrices mark the cutoff points of those two curves. And in this case, in this hyperbola, you would have an asymptote here, and you'd have an asymptote here. They always seem to form a kind of X shape where the meeting point of the X is the center. And they mark the cutting off points of the curve, so the curves don't go beyond these asymptotes. What is the equation of these asymptotes? How do we find what they mean? Well, this is where the constant that we couldn't define earlier arises again. If you've got a horizontal axis, then the asymptote has equation y equals b times x over a, and this asymptote here would have equation y equals minus bx over a. Remember earlier when we were talking about the equation of this hyperbola, we said we couldn't define b. Well, this is where b comes in. B comes in useful when it comes to marking the equations of the directrices. In this case,